Thank you. A very good morning to you. And today I will speak on not on the better known astronomy of Aryabhata, but rather on the tragically neglected, forgotten legacy, which is mathematical legacy of Aryabhata. Okay. And you might say, why does a physicist have to talk about the mathematics? And the short answer to that is I feel very strongly about this. The fact that he is forgotten and he had done such seminal work that him being forgotten even in his own country by teachers and students here is, I think, almost borders on the criminal. Okay. Before I begin, I would like to thank my colleague, a very senior colleague of mine from TIFR, Professor P.P. Divakaran. Professor Divakaran has been the I've had many useful conversations with him about Aryabhata and about Indian mathematics. He's a scholar of Indian mathematics, but he retired as a professor of theoretical physics at the Tata Institute of Fundamental Research. I would also like to thank NCERT. Okay, thank you, Dr. Sunita Farkia, Dr. Gagan Gupta ji, Tanvi ji, for having me over today for this talk. Without much ado, let me begin. Aryabhata's legacy, what Aryabhata did, influenced a whole generation and several generations of mathematicians subsequently. But to understand what the influence that he exercised over Indian mathematics, one must try to understand or get a feeling for the kind of mathematics which influenced Aryabhata himself. And to do that, you will have to go back 1,000 years before Aryabhata and about 3,000 years from now. And this is a map of India. It's not a very good map, I would say, but an accurate map. And you see the green part on the northwest side, that is the Gandhar region, the region of Afghanistan and Pakistan. Basically, that was the cradle where Indian mathematics grew, along with a lot of other cultural activities. The Sutra was written around 800 before the Common Era. It is a geometrical piece of work. The Baudhayana or the Baudhayana theorem is the same as the Pythagoras theorem, predates Pythagoras, that was also developed there. And these are the first two, the Sutra and the Baudhayana, are geometry. Pingala, okay, on the other hand, who lived around 300 years before the Common Era, Pingala took Sanskrit prosody or meter as a prop to develop very beautiful algebraic recursion relations. And so this is an algebraic piece of work which Aryabhata inherited, the recursive thinking. And let me spend a minute to explain what I mean by recursive thinking. For example, in recursive thinking, let me give a very simple example that, for example, if you have a fixed deposit and the bank pays 10% interest, and last year the fixed deposit was 10,000 rupees and the interest was, say, 10% simple interest, then this year it will be 10,000 plus 10% of 10,000, that is 1,000. So now the fixed deposit is 11,000. Next year it will be 11,000 plus 10% of 11,000, so that will be 12,100. So now there is a recursion. You just add last year's income plus add 10% to it, and that's the new income. For every recursion to happen, there are two things which are important. One is, what is the seed? How does the fixed deposit begin? And the other is, how does it end and when does it mature? So there is a seed and there is an end. So, and that is a simple, one of the simplest recursion relations I can tell you about. Pingala did something very similar, but a little more intricate than that. I must also point out to a very important manuscript called the Bakshali manuscript, which was discovered in Bakshali and it's probably predates Aryabhata, I think. And the Bakshali manuscript is the first time you will see the symbol 0. It comes as a dot and now it's a circle. That dot has become a O or a circle right now. Before I proceed, let me also ask you to spend just a moment on the sublime and beautiful statue of Buddha. It's also from the Gandhar region, and there are hundreds of such statues over there, or there were at least. And what I would like to convey with the statue is the fact that not only mathematics, but philosophy and art and culture, that area was the cradle of all this. Okay. Let me continue. Okay. This is a few more examples. The one on the left over here are various weights and measures found in Harappa much before even the Sulb Sutra, and the way the weights are arranged, like 1 kg, say a 1 unit weight and a 2 unit weight, it gives you an idea that they probably knew how to calculate cube roots to an approximate extent. Otherwise, you cannot make a 2 kg weight, cubic weight from 1 kg one unless you knew the cube root. Okay. And there are very beautiful intricate right angular structures in Harappa which tell you that, well, yes, the thinking on geometry was actually inherent and would grew long ago in India. Okay. What you see below here is again from the Sulba Sutra, taking simply a thread or a sulba or a raju and 2 pegs, 2 sticks, you can draw this design. So Aryabhata was an inheritor. He was an inheritor of intricate geometrical knowledge. He was an inheritor of algebraic recursion relations, and he was an inheritor of the decimal system which existed. Okay. And with this, he burst upon the Indian firmament of mathematics around 500 Common Era, 500 CE, that is 500 years, that is about the 1500 years from now. Okay. And what you see is again a map of India, but now what was green earlier is now red. That is because there were hordes and waves of invasions from Central Asia, and they were quite brutal. So people fled, and along with the people, the arts and the mathematicians, they too fled eastwards, and then the center is now somewhere around North Bihar, on the Indo-Gangetic plain is where the center was, and that is where the Aryabhata was written. Okay. The Aryabhata consists of 121 verses only, out of which 33 are in the mathematics chapter, which I will talk about. Okay. There is another 50 on the astronomy, okay. And these verses, you can probably read them in about an hour or two. I mean, it does not take long to read them, but they are so cryptic, terse, and laden with a host of new concepts that to understand them is probably will take you quite a few years. Okay, and that is what I spent, and I am giving this talk now. Once again, I draw your attention to the statue now. The statues are now found in this eastern region, which I have highlighted with green, and this statue is from Sarnath, which is quite close to Patliputra, where Aryabhata wrote this very important manuscript. Okay. So what I would like to convey to you is not just the mathematics, the art, the literature, the culture, the sculpture, they all shifted eastwards as time went on. Okay. Let me continue with the introduction. This is again the Aryabhata, as I said, has been honored with a host of commentaries by the preeminent Indian mathematicians, Brahmagupta, Bhaskara, Bhaskara II, and Nilkantha Somayaji, all the way down in the deep south along the banks of the Nila river in Kerala. They all have had something to say about the Aryabhata. It created such a big impression on Indian mathematics that they had to understand it before they proceeded forward. There are 2 translations that I would like to draw your attention to, one by Clark and the other by Kripashankar and K.V. Sharma. The translation with notes, this is an INSA publication from 1976 that you might want to look at after my talk. By the way, this map and this sculpture of Aryabhata, or this has been actually, they are taken from the Survey of India and from Ayuka, Pune. So much for the introduction. So now let me launch into the mathematics and why it is so, and give you some flavor for the kind of mathematics that Aryabhata developed. Okay. Aryabhata defined what is called the sine function, and this is the first in mathematical history. Okay. And with that, I think he established himself as the founder of trigonometry, but I will continue further with this. He says that you look at the circle, I have a unit circle, you look at this circle and you draw this chord AP. I mean, you just draw this half chord. So he says this chord AP is the ardhajya meaning half of the sine. Okay, half of the chord is what is important, he says. what is important is not the full chord, but it is half the chord. Okay. And the sine function is defined as this length AP divided by the length OA, which is the radius, but the radius is 1. So, the sine theta is simply AP. Okay. Aryabhat, I would like to tell you, and I would like to make a disclaimer here, Aryabhat does not take a unit circle. His circle is of length 3438 for a reason that we will come to in a short while, and what he has is something called an R sine function. So, instead of the radius being 1, he takes the radius to the right hand side over here. He has R sine theta and his R is 3438. I am using a modern notation, and I beg your indulgence because I believe that all of us have done some physics, and you know that in physics you can get hung up on units. You can get hung up on the fact, is the energy in kilocalories, I eat about 2000 kilocalories, or is it in calories or in joules or in ergs or in electron volts, but if you get hung up on that, then you will miss the essence. So, I would say that you bear with me, I will take the modern notation and I will use a unit circle. Okay. This is, as I said, the first time in mathematical history. Now, you might say, what is so great about this? I mean, you defined as half chord. So, the answer to that is the following. The first answer to that is the circle can be large, it can be small. This half chord can be large or it can be small, but this ratio of the half chord AP to the radius OA is invariant. That does not change, that whatever the size of the circle. So, you have an invariance here, and in physics and in science and in mathematics you look for invariances. The other point has been made by John Playfair way back in 1798 when he was exposed to Aryabhata. He says there is a big difference between trigonometry and Euclidean circle geometry. What he meant by that was the fact that when you look at the sine function and the cosine function, every metrical property of the circle. Now, what do I mean by a metrical property? You draw a quadrilateral or a triangle inside the circle and you say, give me the relationship between one side and the other sides, or between the sides and, say, for example, the diagonal. They can all be expressed in terms of the, or derived in terms of the sine and the cosine and the trigonometric function. So, you endow circle geometry with measurement properties, and the sine function and the cosine allows you to do that. Okay. So, that is the difference. With this just one definition, Aryabhata would have qualified as the founder of trigonometry, but he did more. Okay. Okay. So, now we begin. Now, let me just backtrack a little bit and tell you one or two things before I proceed. This is the angle theta. Okay. If, for example, you went all the way around and through the half circle, that would be the angle 180 degrees. We all know that. In science, we call it pi radians. It is measured in radians. So, this 180 degrees is pi radians. What is XOY, the right angle triangle? In science, it is either 90 degrees, but we prefer to use and call it pi by 2. Okay. The other thing you have to realize, and Aryabhata gives you this value of pi, as was very correctly pointed out by Vijay in the beginning. Okay. The other thing that you can notice right here, without knowing any mathematics, is that if the theta angle is small, then AP is small, and the arc XA. So, notice the arc XA and the chord AP will be almost equal to each other. So, what Aryabhata implicitly does in his work is that he takes sine theta to be equal to theta when theta is small, and this is something that we do after we learn calculus, but you can also understand it by simply looking at this figure. Okay. That when theta is small, the half chord AP is equal to the angle XA. Okay. Okay. So, the next in Ganita 10, or the 10th verse of the Ganita, Aryabhata gives you in black and white the value of pi. He tells you this pi is nothing but 62,832 divided by 20,000. So, his value is 3.1416. He just gives it to you, and where he pulls it out, probably he did some measurement and he got this. It is not very clear. As I said, these words are very cryptic and final answers are given. Okay. It is the whole Indian tradition has been Shruti and Smriti. I mean, the verses are just going to be given to you, you work it out later. Okay. But Aryabhata is very clear in this, and he says this 3.1416 is not quite the value, it is asanna. Asanna means proximate, it is not sthula or approximate. He says you can, what does asana mean? Asana means there could be a few more decimal points after this. It could be 3.14158 and so on and so forth. Okay. So he says I am giving you an approximate value good enough for me and good enough for us and good enough for our astronomy at the moment. Okay. But it is, please bear in mind that it is approximate. For example, when you say the mass of the electron, for example, and as a theorist I say it is 10 to the minus 30 kg, that is stula or approximate. But if I am an experimentalist measuring the mass of the electron, I will say 9.10938, with the understanding that if I have a better experiment, then it will go 9382371, some other decimal places will come after that. Okay. So he is clear about this fact that there is an so-called hinting that it is an irrational number. Okay. The next thing he tells you is that I have defined the sine function for you. Now let me tell you, give you at least one sine function, and he gives you the sine function for 30 degrees. He says the sine of 30 degrees is half, and it is right here. 90 degrees I said was pi by 2, sine of 30 degrees is pi by 6, sine of pi by 6 is half. He proves it in a very simple way. He just dismisses it in no time by saying if you look at this side OX, which is a unit circle, and you draw and you basically make 60 degrees, you draw another arc, another radius OP, which is also a unit circle. Since this is 60 degrees, this angle, the other two sides being equal are also 60 degrees, 60 degrees. It is an equilateral triangle. So the angle, so the side XP is also equal to 1, and half of that angle XP prime, half of that chord, sorry, I am sorry about this, half of the chord XP prime is also, is just going to be half. Okay. So he just gives it to you. One sine, he said I am giving you one sine function, but wait, he says very soon I will give you a sine for any angle you want. Okay. There is one other thing I have to tell you. He uses a very small angle in this in his work later on, and that angle is pi by 48, which is 3.75 degrees. Okay. And for some reason, I mean this is an archaic notation you might say, he uses minutes. 1 degree is 60 minutes. So pi radians is 3438 minutes, that is his radius, okay, and therefore 3.75 degrees is just nothing but pi by 48 multiplied by 3438, and that is 225 minutes. Okay. Keep that in mind as we move along. Okay. So this is Ganita 11 and this is Ganita 10, where he tells you the value of pi, and he defines the sine function implicitly earlier as the ardhijya. So now we come to what I would call Aryabhata's masterpiece verse, Ganita 12. Okay. What does he do in Ganita 12? Okay. We cannot go through the entire algebra over here, but I can give you a feeling for it. Okay. What he says is the following, and if you are a student, I would like you to pay attention here. What he says is you take this unit circle and then you take this angle theta, okay, and you subtract a small angle phi from it. So what you have over here as this arc XB, it defines an angle theta minus phi, which I have shown over here. Similarly, you define an angle sine theta plus phi, and it's also, although like a magician or the wizard, he pulls it out of his hat, out of his just as the wizard pulls it out of his hat, he pulls it out and he says sine of theta plus phi, that is sine of the mean angle theta minus the small angle phi minus the sine of the small mean angle theta minus the small angle phi is equal to 2 times the sine of the small angle into the cosine of the mean angle. Okay. He just this is just one of the things stated in Ganita 12. How does he prove it? The way he proves it is something that I cannot get into, but it is all here in black and white. If you look at this, if you just pause it later in your YouTube, it is all there. It is basically right here. What he says is, I will draw 3 chords, half chords, this AP, BQ and CR, these are the sine functions, and by showing that the two triangles BSC and OAP are similar, I can prove this, he says. Okay. So we are not getting into this proof, but the fact is to think of this difference of signs and to think of the fact that you can prove it by similar triangles would be something which would be beyond any normal intellect. Okay. But he does something more with this, and this is very striking. And it just has been a big puzzle how he managed to do it. He calls this angle theta minus phi, which I had earlier, this is the same diagram as earlier, so I am not doing anything new, okay. And this is the same formula as earlier, so it is nothing new. He calls this theta minus phi as some integer m minus 1 epsilon, and theta plus phi is m into epsilon. So he defines a small angle epsilon and he calls it m minus 1 and m plus 1. So what he is doing is the following, he is going in steps from very close to 0 degrees, he goes in steps all the way up to 90 degrees by defining in steps of epsilon. Okay. And the sign of theta minus phi, let me call it s m minus 1, which is right here, and the sign of theta plus phi, let me call it as sm, and he expresses the difference of these two angles in terms of the sine of the small angle and the cosine of the mean angle, something that you saw it right here in the cosine of the mean angle. So I am using a notation in which is slightly different from Aryabhata's or from whatever his commentators were, so that we can understand what is going on. However, so basically I want to reassure you that this difference equation that I have written is the same as one I had presented in the previous slide, but he is not satisfied with that. He takes the second difference, okay, and he writes the second difference not in terms of the cosine, but in terms of the sine function. Okay. So I want you to pause. Basically this algebra is a little heavy for us, but the technical aspect will escape you at the moment, but essentially what he does is he takes the second difference. Okay. Now why he does it and what are the implications of this is what I would like to tell you in a short while, but right now I want to pause and I want to tell you something which has been puzzling me for a long time, and I asked a few people about it, and he says that I said there is only one verse, okay, there are no diagrams, and there are no equations and there are no formula, okay. And how did Aryabhata even conceive of this, and even if he conceived it, how did he explain it to his gifted students? So at one point a person got exasperated with me and he said maybe what he did was he went to the banks of the Ganga, because he was in Patliputra, he went to the banks of the Ganga and he said when he drew in the sand he must have drawn these circles and tried to explain. And so I tried a similar exercise with my students from the Center for Excellence in Basic Sciences. So these are gifted students. I drew a circle and I tried to explain how Aryabhata could have conceivably derived these formulas, and I tell you I failed. I mean they just couldn't understand what I was trying to do. Okay, this is me and these are my students. Okay, so I believe only a phenomenal combination of abstract thinking and inner eye visualization and fantastic I would say memory can get you through in this. Okay. So this one verse. Okay. And then finally what Aryabhata does is derives a recursion relation with the same second difference. This is the second difference of sine theta plus m minus sine theta minus m. It is in terms of the first difference, a previous difference, and in terms of the sine function. And he expresses, then he does something which is very absolutely another thing which you would not think of. He takes this Sm minus 1, he subtracts Sm minus 2, he adds Sm minus 2, subtracts Sm minus 3, adds Sm minus 3, and addresses the difference of the sign in terms of the difference of the signs. So in effect he is getting a recursion relation for the difference of second difference of signs in terms of the second difference of sign. So this is the recursion relation which I talked to you earlier about, that to start a recursion you must know how to start this recursion and you must know how to end this. Okay. And what he does is, to start the recursion he says delta S1. Okay. What is delta S1? It is S of epsilon minus S of 0. S of 0 is 0, S of epsilon is epsilon. So this epsilon which I had just told you right now, right here. Epsilon is just 225 minutes. Okay. And he also gives you the second difference, so you can continue with the recursion. How do you end the recursion? Very interesting and not noticed even by I would say certainly not by European mathematicians for a long time, that he said the sine function is periodic. So he knows that after 0 to 90 degrees you have to stop this recursion, because then you will be repeating it. Okay. So it is almost like how should I tell you? I mean the way I can convey it to you is, you need a seed and you need to stop it. Yes. Okay. and he stops it by saying that it's periodic. So I can tell you a story about it, which might interest you. There is a king. Okay, there is a kingdom. There is a fisherman. The fisherman finds, for example, a beautiful pearl when he cuts open a big fish, and he says, "Who deserves it?" He gives it to the most deserving person, and that's the king. The king takes it and says, "Who deserves it?" He gives it to the most deserving person, who is his wife, Pingala. And what does the queen do? The queen has got something going on, and she thinks the most deserving person is the general. He's so handsome and he's so brave. She gives it to him, and the general is very enamored of the court dancer, so he gives it to the court dancer. And the court dancer then says, "Who is the most deserving person in the kingdom?" And that's the king. So it's a periodic solution now. What was the seed? The seed was the pearl. And what is the recursion? The recursion is to give it to the most deserving person. How do you end the recursion? It goes back to the king. Okay. Now the king can do the same thing. He can give it back to the queen or whatever it is. But what he really does, he realizes that the meaninglessness of life and love, and he becomes a recluse and a sannyasi. Okay. So that's what it is. So you start a recursion and you must know how to end it, and that's what Aryabhata did. Okay. So much for the mathematics of Aryabhata, and this very intricate and beautiful verse, Ganita 12, which has all of this buried, and it's not something that I have cooked up. It is there in Nilkanta Somayaji's commentary in 1450 Common Era. Okay. And I have taken it from there. It's also there in the work of Kripa Shankar Shukla and K.V. Sharma. So you might say, okay, so he defined a sine function, and what are the implications of this Ganita 12? Okay. So let's look at the implications. So now again the mathematics is gone, and I'll make it very friendly to you. He says, look at this, what he did first. You take theta plus phi minus sine of theta minus phi, make phi equal to theta. Then you have sine of 2 theta minus sine of 0, which is 0, sine of a 0 angle is 0, that is equal to 2 times sine theta cosine theta. And similarly, cosine of 2 theta minus cosine of 0 is equal to minus 2 sine square theta. So he has the half angle formula. So Aryabhata has the half angle formula. He defines the sine function. He gets you this very beautiful recursion relation for the sine functions, which implies that he knew the half angle formula. But he did more. Okay. He generated the entire sine table. Okay. And it's right here, and it is to be found in his Aryabhatiya. He says the sine of 3.75 degrees or 225 minutes, sine of epsilon is epsilon, sine of 30 degrees, which is 1800 minutes, is 1719. Sine of 30 degrees is half, I tell you. But if you use r to be equal to, radius to be equal to 3438, half of 3438 is 1719. So he gets it right there. And when you compare Aryabhata's sine table with the modern values, the difference is very, very small. Okay. So it almost agrees with what the modern values are. So his method for calculating sine differences was used for 1,000 years by Indian astronomers, astrologers, and mathematicians. Okay. He also realized that you don't need to go beyond 90 degrees. He also realized that if theta is small, sine of that angle is equal to itself. Okay. So he had all of this. And what I would like to tell the audience here is that every time you look up a sine table or a trigonometric table, and every time you click on the calculator, okay, you must say a silent thank you to Aryabhata for having shown this way. This is for the first time that you see the sine table in any mathematical literature. Okay. All right. So can I continue? Is it showing?
Yes, please. Yes.
Because it's not coming there.
Don't worry. It will come.
No.
It will come.
All right. So, okay. Then there are yes.
One point in between,
yes.
sir. Can we take to the last slide, please?
Yes,
slide
yes.
14.
Yes.
Yes. So here I am getting a query from some child. You mentioned that sine theta, the sine of a theta is equal to theta, roughly equal to theta.
Yes.
As theta goes down.
Yes. Small.
Small. So this theta is, friends, in radians, not in degrees.
Yes. Yes.
This please. I mean, the query of the child was
yes,
that
it is in radians.
confused.
Yeah.
It's in
I
radians.
said it,
Yes. So please continue,
Very
sir.
good. Thank you for the
Please continue,
clarification. And maybe I was not clear, so I apologize.
No problem,
But yes,
sir. No problem,
sine of theta is theta if theta is in radians and small. Okay, but Aryabhata for some obscure reason multiplies it all by 3438. Okay, that's the reason is very clear. Pi radians is equal to 3438 minutes. Okay. Then I had told you about Ganita 10, Ganita 9 and Ganita 12. Okay, one of them is the definition of pi, the other one is basically a sine of 30 degrees, and Ganita 12 is a masterpiece which gets you the sine table. But there is Ganita 11 that I missed, and there is one phrase in it which became very important, and he says, Aryabhata says I have taken epsilon to be pi by 48, okay, a small angle as was just mentioned by Gaganji, 3.75 degrees, 225 minutes. But there is no need to take that, you can take it whatever you want, you can take it as small as you want or as large as you want. So, Brahmagupta much 100 years later took it to be 12 degrees and generated his own sine table. Okay. But 1000 years later, on the banks of the Nila river, Madhava and his disciples and a string of very eminent and brilliant mathematical disciples of mathematics took this to be very, very small, and with that they developed the calculus of trigonometric functions. So, the calculus was discovered, and I am not saying Aryabhata discovered it, Aryabhata hinted that you could take epsilon to be small, and these people actually took it to be very small and was able to do the entire how should I say rigor of calculus. With entire rigor they developed the calculus of trigonometric functions. Okay. So, not to detract from Madhava's work, Madhava they still regarded Aryabhata to be a Param Purvacharya. They are actually indebted to him, they say, but this was a brilliant piece of work, probably one of the last important pieces of work to come out of Indian mathematics. Okay. The other thing is, since you can take epsilon to be small, the difference of the signs Sm minus Sm minus 1, which I have written here as sine m epsilon minus sine of m minus 1 epsilon. Look at this quantity, sine of a small quantity is epsilon by 2, the 2 cancels out. So, you are left with epsilon, bring that epsilon down here, and what you are left with the cosine of the mean angle. So, this is what is now known as finite difference calculus. If you want to do numerical methods and if you have to take derivatives, this is what you do. And if you want to do the second derivative, it is the second difference that Aryabhata did, and you do it once again and you get the second derivative to be equal to minus sine of x, d square sine x by dx square is minus sine x. So, the seeds, or in a sense there is finite difference calculus buried in this work. Okay. I am not saying he said those days there was no calculus, so there is no point in talking about finite difference, but if you look at it, I always found it as very fascinating that you take the second difference of the sine and you get minus of sine. Now, why is that second difference important? Newton's second law is a second difference, okay. And the Schrodinger equation in one dimension is also second difference, and simple harmonic motion, this is the solution, d square psi is basically d square sin x by sin square x is minus sin x. The second derivative of x with respect to time is equal to x, minus of x. So, a lot of this is basically I found, this is my observation, I mean I found it very interesting that there is finite difference calculus buried in this verse. And finally, as I said, mathematics travelled south, okay, calculus. Okay. You see the same map of India, but now what was green is now red. Okay. Because once again there were waves and waves of invasion, okay, and they were brutal, there was massacre, there was mayhem, and people fled again. So, they first fled somewhere to central India, which is somewhere around here, Brahmagupta, Bhaskara 1, Bhaskara 2, you will find them all around this region commenting on Aryabhata, and then it moved south on the banks of the Nila river in Kerala. Okay. So, the Madhava and the Nila school is to be found over here, and that is where it went. But let me backtrack and come here to central India. You see this once again, you see the sculpture. See the sculpture from Ajanta. Okay. It's similar to what you would find in the Gandhar region, and similar to what you would find in Sarnath, similar to what you would have found in Mathura, and now you find it approximately 500 CE, 600 CE in the Kanhari caves of this. For example, look at this statue. This is from the Kanhari caves near Mumbai, okay, from my own backyard where I teach. Okay. It is the statue of what is called the travelling Buddha. So, in a sense what is happening, and Tanviji, what is happening here in a sense is something very interesting, since and I draw your attention to this. The travelers are travelling through forest, they are travelling through rivers and crossing mountains, okay, and they are thanking the Buddha for bringing them to a safe passage, say to the banks of the Narmada. Okay. And what you see on these sides are basically statues of lions, snakes, fires, etc. So, the statue is also called Ashta Mahabhaya, that is, I am thanking the Buddha for saving me from the 8 great perils as I travelled, okay. Flash floods, forest fires, reptiles, carnivorous animals, plunderers, traps, demons, and what have you. Okay. So, these stones also carry a story with them. It is a very sad, tragic story that the stones tell you they are silent, but they carry the story of this travelling. Okay. So, basically, when Madhava developed along with his disciples this Kerala school, I give you only one example. I cannot do justice to it, and I am not even sure if I did justice to Aryabhata, but at least I have conveyed some sense of what my passion for it. They derived this value for pi by 4, okay, and this value, the expression for pi by 4 they write as 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. You can continue it, and you can do it on the calculator and satisfy yourself that you will get a value very close to pi by 4. This can only happen if you know how to do an expansion of tan inverse, the inverse of the tan function. What is the tan function? The sine function divided by the cosine function. And you can do that expansion only if you knew calculus. So, that is a hint, and that was actually noted by Charles Wish in 1834. He was very surprised to see this Gregory Newton formula in some Malayalam text or something, or Sanskrit text in Kerala, and he said these guys had calculus, so to say. In fact, not only did we have calculus, we had the calculus of trigonometric functions, which actually predates Newton by about 200 years. Okay. But we also held, and this is very important, we held the world record for the calculation of pi up to 18 decimal places, okay. And that was held by Indian mathematicians, Shankara Varman, by Indian methods of calculus, not by foreign methods. Okay. Nowadays you see in newspapers once in a while an announcement, now pi is known up to some 10 trillion places or something. In 1800 we had the record. So, what is the tragedy of Aryabhata? I have come to the conclusion of my talk. I believe I have another 5 minutes.
Yes.
Thank you very much. Yes. Okay. So, the tragedy is that empty praise. Okay. We basically say he was great, implying that we are also great, but we do not know why he was great. He was great because he founded trigonometry. Endless debate on pointless issues. When you come to Aryabhata, where was he born? Was he born in Kusumpura or Pataliputra or in Narmada or wherever he was, and was he rector or chancellor, where was his observatory? This yes and no has gone on for too long, and I find them very irksome. Okay. The focus on Golapad to the neglect of the Ganitapad, except for is also, I think, tragic, because the Ganitapad has the has trigonometry in it. Okay. But the Ganitapad has one more extra thing. Aryabhata has the solution for the linear Diophantine equation in his shloka 32 and 33 of the Ganitapad by the Kutaka method, and I would have spent some time on it, but there is not enough time, right?
Enough time,
no, so I will not spend time on this. So, we have these exaggerated claims of Aryabhata which are not, I mean, there is no need to make it. You just make one claim, and that is he founded trigonometry. And by the way, he also made some very important observations in astronomy, basically saying that the earth is round, something that was known earlier also, but what was not known was the fact that day and night, he says, is because of the rotation of the earth, and because of what is called relative motion, you think that the sun is going around, but it is actually the earth which is rotating. And then he also talked about eclipses. He said eclipses are shadows, they are not some mythical monsters like Rahu and Ketu. So, if you believe Aryabhata, you should stop believing in these myths about eclipses. Okay. So, I will not spend time on this Diophantine equation. So, let me continue with the tragedy of Aryabhata. He has been misunderstood by scholars such as Al-Biruni, Brahmagupta, even Brahmagupta by the way, and in the West. And I think part of the problem was that his style was terse, cryptic, and it was loaded with new concepts. He got the half angle formula and no more, wrong. His chord is the same as the Greek master's chord, no, it is the half chord, and trigonometry is very different from geometry, Euclidean circle geometry, no sine function, no Snell's law, no force components. The list is very long. He proposed proto-trigonometry, that is what they would grant, wrong again, he founded trigonometry. The geometrical methods used by, and I believe the real tragedy is coming now, and I am in NCERT, so I am speaking about it. The geometrical methods used by Neelkanta Somayaji to establish trigonometric recursion relations are accessible to high school students, and we should tell them about this in 10th standard. We are cutting down the syllabus, but you should add this one thing and should be taught as such. When teaching trigonometry, one should at least, I think, acknowledge the great master as the founder of this subject. Okay. Little do we know when we look at the sine table or use our calculator to get the numerical value of cosine or sine, how much is owed to Aryabhata. Okay. And the final thing is basically Aryabhata for me signifies a unifying thread in Indian science and mathematics, because what you see is an overarching unity in Indian mathematics and astronomy with Aryabhata as the binding cord. He learns from what was in the Gandhar region, and the reverberations of what he discovered on the banks of the Ganga in Pataliputra was heard 500 years later, Bhaskara too, on the banks of the Narmada, and 1,000 years later on the banks of the Nila river. Okay. So, there is one unity, and that unity is that of mathematics. Okay. There is another one which has been a constant backdrop to my lecture, and that is the sculpture. You look at the sculpture, this temple in Almora, okay, and
Yogeshwar temple.
No, there is not the Jageshwar temple. There is another temple. Okay, and there are, by the way, at least 100 temples over there of this variety. Okay, and recently one of them was in the news, the Kutumkuri, which has been destroyed stone by us. They have taken this temple and destroyed it by taking these stones and building their own lavatories or toilets and houses. Okay. That is how sad it is. And you see this temple, and you see another temple here in Kurnool, Andhra Pradesh, and they are similar. So, you see the unity not just in sculpture, you see the unity not just in philosophy. Okay. Buddha was, Mahayana Buddhism propounds Shunyavad. Okay. Shankara's guru what is his name? Shankara's Gaudapad. Okay. He was also called a Prachanna Bauddha because he advocated Advaita, or single God or something. Okay. So, Shankara brings this down, and then the same Shunyavad travels back to the north. So, there has been a proper unity in religious philosophy. You learn from the Buddhists, you bring into what is called Hindu philosophy or something, and then the Sufis take it from you. So, there is a unity over there. There is a unity in literature, but there is also a great unity in the Indian mathematics, and Aryabhata was the binding cord. Okay. So, this is the references. As I have already mentioned, I am very indebted to this book by Kripashankar Shukla and K.V. Sharma, and also most importantly these two authors basically who revived Indian mathematics, Vibhuti Bhushan Datta and Avdesh Narayan Singh, History of Hindu Mathematics. They were from Lucknow University. Mind you, they are not from IIT or some famous university or something. They actually worked on it, and that time at Lucknow University for a while the Vice Chancellor was a great man, great historian, Acharya Narendra Dev, a socialist and a historian who encouraged them to do this. There is another historian of Indian mathematics, Saraswati Amma, geometry in ancient and medieval India, which you might also want to look at. But the one book that if you really want to read is the one by Divakaran on the mathematics of India, because that will explain to us at our level. It is not an easy book to read what this whole thing is about. About Aryabhata and about Madhava. I also have written an article on it which is not yet published. Okay. I have a YouTube handle, and Physics Sutra official, where the Kutaka method is described in terms of Bhojpuri, how should I say, Bhojpuri riddles, in terms of riddles, 10-minute riddles. So, if you would like to know understand the Kutaka method, it is right there. Okay. Finally, I will rest with this. What Aryabhata does is something very interesting. You might say, what kind of a person was Aryabhata? Certainly he was a scientist. He was very scientific about it. And there was no false modesty in him. He acknowledges Brahma as the Nirgun Brahma, and then he says, this knowledge has been brought out to me by my intellect from the sea of true and false knowledge by diving deep into it. So he says, it is my intellect that I have used to arrive at this knowledge. Thank you very much.
Thank you very much, Professor Singh. बैठे बैठे खो गए हम और लग रहा था कि ये चलता रहे पर आई वॉज एन्जॉइंग इट. मैं तो बिल्कुल डूब गया. मुझे मालूम ही नहीं पड़ा कि कब ख़त्म हो रहा है और रियली आई एन्जॉयड इट लॉट.